Hey there, ladies and gentlemen. Making a video here on the answers to the review worksheet. First couple questions here are pretty simple. We're just converting between calories and joules. Yes, you do need to know that 1 calorie is 4.184 joules. This is also related to the heat capacity for water. The heat capacity for water is 1 calorie for every 1 gram degree Celsius, or 4.184 joules for every gram degree Celsius of water. So heat capacity for water and this relationship between calories and joules are all interrelated. So all we're doing here is just using dimensional analysis to go from calories to joules. So I have 45.8 calories, 1 calorie is 4.184 joules, 192 joules. Half a calorie would be about 2 joules. 59,000 joules to kilocalories. So the first thing I did is I converted joules to calories, and then I used the fact that 1,000 calories is 1 kilocalorie to convert it over to kilocalories. And lastly, 76 joules is 8 calories after you do sig figs and stuff. Yes, you should do sig figs always. Number 3, we're using the Q equals MCAT equation. Q is energy, M is mass, C is the heat capacity or specific heat, and delta T is the temperature change. The temperature change is always the final temperature minus the initial temperature. So in number 2, I've identified all the values. We have our Q, looking for it in joules. We have our mass. We have our temperature change. 50 minus 25 equals the delta T of 25. We have our heat capacity of carbon, which is 0.71 joules per gram degree Celsius. Plugged them all in and calculated the amount of energy. Since the delta T is a positive value, the temperature is increasing, then our energy value should also be positive, because if the temperature is rising, then the energy is rising. Number 3, we're supposed to calculate the energy in calories. Did I calculate it in calories? No, I did not. I'll have to do that in a second. So I have 10 grams. And then my heat capacity is joules per gram degree Celsius. And then my delta T is in degrees Celsius. So my grams, my Celsius cancel. So this answer is in joules. And the problem with that answer is that the question clearly says in calories. So let's do that. 160 joules. And what should go on the bottom? Yep, you in the red shirt? You are right. You are right. 4.184 joules is 1 calorie. So we need to grab a calculator. I have this one here, 160 times 1 divided by 4.184 is in 2 sig figs. It's 39 calories. There we go, 39 calories. Yeah. Number 4, how much energy is required in both calories and in joules to raise the temperature of 1 liter of water from 0 degrees Celsius to 100 Celsius. So first of all, the heat capacity for water is one of those things you need to know, so that's what I worked out first. The heat capacity of water is a calorie per gram degree Celsius, or 4.184 joules divided by grams degree Celsius. I chose to start by using the heat capacity in calories per gram degree Celsius, not in joules. The next thing a lot of people want to know about is the mass. How did I get that it was 1,000 grams? So a liter of water, let's go over here, people. We'll zoom in for those of you who can't read small handwriting from a distance. A liter of water is the same as 100 milliliters. I mean, 1,000 milliliters is the same as 1,000 grams, because the density of water is a gram per milliliter. And if you zoom in on this pen thing, it doesn't look too good, does it? So I put 1,000 grams in, and then the last thing we were supposed to look for was the delta T. The delta T is how much the temperature is changing. It's going from 0 to 100, so that's an increase of 100. So then I multiplied 1,000 for the mass times the heat capacity, which is 1, times the temperature change, which is 100. That's 100,000 calories. which is the same as 418,400 joules. Yay! So I worked it out in both calories and joules that time. For number 5, please look at question 2. They're the same. There you go. Okay. Question 6. How much of a temperature change would occur if 2,736.8 joules of energy, that's pretty specific, were applied? So there's energy going in. So this is a positive value. It's being applied. If the bar weighs 50 grams, that's the mass. The heat capacity of the iron is 0.45. That's our C. The iron started at 25 degrees Celsius. What would be the final temperature? So I usually, if I'm trying to find a final temperature, I will set up the Q equals MC delta T, and I solve for delta T first. So that's what I did. I plugged the values in, and I found my delta T was 120 degrees Celsius. It means it's going to increase by 120 degrees Celsius. It started at 25 degrees Celsius, so 25 plus an increase of 120 is 145 degrees Celsius. Number 7, we had to talk about whether things were endo or exothermic. Again, endo means that it's taking energy in. Exo means it's giving off more energy than it's taking in. So photosynthesis is definitely endothermic. It's taking light energy in and converting molecules into complex things. Running is definitely exothermic. You are giving off lots of heat and burning lots of fuel. Melting snow is endothermic. You're putting energy into the snow and it becomes a liquid. You're breaking bonds. It's melting. It's endo. Cooking pancakes. I had a couple people ask me questions about this. I'm not asking from the pan's perspective. I'm asking from the food's perspective. From the food's perspective, it's endothermic. You're putting heat into the food and changing it by heating it. So it's endothermic. Rain from water vapor. Some people don't understand this. I'm not sure about those people. But let's just rewrite this as condensation. If you take a gas and you turn it into a liquid, you're not putting energy in, you're taking energy out. If you want to turn a liquid into a gas, you'd put it in. If you take the energy out, you're turning it back, you're condensing it. This is exothermic, getting rain from water vapor. Combustion is definitely exothermic. When you burn things, combustion is synonymous with burning or explosions. Definitely exo. Those chemical hand warmers give off lots of heat. They're definitely exothermic. And the chemical cold packs are endothermic. They take heat in when you hold them. That's why they feel cold, because they're taking heat in. They're endothermic. 8 is actually a two-part question. So I first, above the squiggly line, above the line we have the water's perspective. So you have 60 milliliters of water, which is the same as 60 grams of water. You have the heat capacity for water, which you should know. We have the delta T for water. The delta T was initially at 22, final is 28. 28 minus 22 is a delta T of 6.5. So the water has gained, that's positive, has gained 1,631.76 joules. Where is the water getting its energy from? The metal. This is just like the lab we did. So the metal is losing the energy that the water gained. Say that again. The metal is sitting in water, and the metal is giving energy off into the water. It is losing 16,000. So the water is gaining 16,000. And I know I just wrote 1,600, not 16,000. But as the metal loses, the water gains. So those two values should be equal, but opposite in sign. So for Q, I plugged in negative 1631. This is the mass of the metal. Don't know the heat capacity. This is the other thing that throws people off. The metal was in boiling water ahead of time, so it was at 100, and it's finishing at 28 degrees Celsius. So it drops in temperature by 71.5 degrees. So we have a negative Q here, and we have a negative delta T here, and when the negatives get divided into each other, they cancel out, and we end up with a heat capacity for metal of 0.382 joules per gram degree Celsius. Hey, Mr. Murphy. Yes, guy in a blue shirt. What if I don't do the units right? Well, then you're going to lose points because units matter, right? Right. Okay. So you do have to get those units right. We have divided the joules by the grams when we moved this over here. We're dividing this over here, so we're dividing by the grams, and we're dividing by the degrees Celsius. We're dividing them underneath the joules also. So it's joules divided by grams and degrees Celsius, which is why all three units are in that answer. Number 9, what kind of energy is stored in chemical bonds? Potential energy. What is the law of conservation of energy? Energy can never be broken or destroyed, created nor destroyed. I said broken. It just moves around from one substance to another substance. What is entropy? Entropy is a measure of disorder. So which of these has the most entropy? Which of these has the most disorder? Which one is the craziest, most wild? So a block of iron, the atoms aren't moving very fast. Liquid water, they're moving a little bit faster. But air, the particles are moving the most. They are not connected in any way, so they're definitely the most disorganized. And on this question, we can tell if it's endo or exothermic by looking at the sign. The ones that are positive are gaining energy. The ones that are negative are losing energy. And what else do we have in here? Missing. Oh, that's good. That's all we wrote. With these guys, we often looked at graphs also. Which of these is an exothermic graph? Which of these is an exothermic graph? Exo means it's losing energy. That would be this one. So it's actually losing energy. This is the potential energy, and this is like time. And so it's definitely losing potential energy. That makes this one, where it's increasing potential energy, the endothermic graph. So this is endothermic, and that was exothermic because it's going down by the end. Alrighty, that is your energy review sheet. Good luck, ladies and gentlemen.